Section 8.6, Vector Operations. And so in this section, we're going to look at performing calculations with vectors, and we're only going to look at a portion of this section. I'm not going to go very deep into it, but just at least give you a little bit of idea of how we can do calculations with vectors, different forms or formats that we can use to express vectors or represent vectors. And of course, vectors have a lot of application in real-world situations, a lot of physics type applications, those types of things. But they are very useful beyond just mathematics. So first, we're going to start with our what we call our position vector, and this is we talked about vectors in the previous section when we talked about equivalent vectors, and we said every vector that has the same magnitude and direction, right, would be equivalent, and that there were an infinite number of equivalent vectors to any given vector. And I said the one that was of most importance or most interest would be that vector whose initial point is at the origin, right? And we could use that vector to represent all of the vectors that are equivalent to it, right? But it makes it a little bit easier to work with if the initial point is at the origin and the terminal point is then at some point in the plane, give it coordinates a, b, so that this vector v can be represented simply by identifying its components a and b. And when we talked about, remember, the components of a vector, we said every vector has a horizontal and vertical component. The horizontal component of your vector would be the length of that side of that triangle, which is the value of a. The vertical component of your vector would be the length of that side of the triangle, right, which is the value of b. So the components of the vector then would correspond to the coordinates of that terminal point for the vector whose initial point is at the origin, right? And so that's the idea. So if I can then refer to that point AB as the components of our vector V, or say the vector V having components AB, and then work with it that way. All right, so the language. We call this a vector in standard position. Vector V is in standard position. Change that. It has its initial point at the origin. It's also called a position vector. So when we talk about the position vector, that's the vector whose initial point is at the origin, and it represents all vectors that have the same horizontal and vertical components. So its terminal point lies at a point AB, and that point can then be used to define the vector. And then to distinguish the vector from a point or interval notation, instead of using the parentheses, we use that little symbol to represent the vector. So vector V having components A, B. And again, it's horizontal component, vertical component, just as you would list an ordered pair X and Y. But the notation that we're using there instead of the parentheses to distinguish between the point in the plane and the vector whose terminal point is located at that point. So this is called the component form of vector V. A and B are scalar quantities. Remember, scalar quantities are just values, right? It's the horizontal and vertical components of your vector. The position vector V having components A, B represents all vectors with a horizontal component of A and a vertical component of B. Right, so this is what we had kind of talked about in that previous section. If I take, say, vector AB, the one on the left, the component form of vector AB with point A, its initial point, having coordinates x sub 1, y sub 1, and its terminal point, point B, having coordinates x sub 2, y sub 2. So I could represent vector AB having horizontal components, which is the change in the x coordinates between those 2 points, right? That's the horizontal component of your vector. So x2 minus x1. And then the vertical component, the change in the y coordinates, right? So y2 minus y1. So then this vector OP, if I take vector AB and just slide it down to where that initial point is at the origin, I get vector OP. which is equivalent to vector AB, it has the same horizontal and vertical components. Right? So we say then that this vector OP represents all vectors that have the same horizontal and vertical components, of which vector AB would be one. So notice, in order to get the vector in component form, all you're doing is taking the difference in the x coordinates for your first component and the difference in the y coordinates for your second component between the initial and terminal points of the vector. So call this the component form of your vector. So if I have point A located at 1, 4, and point B, whose coordinates are 3, 7, then vector AB has a horizontal component of A equal to 3 minus 1, or 2, and vertical component of B equal to 7 minus 4. Not what I want. A is 3 minus 1, or 2, and then B is 7 minus 4, or 3. Now, it's always the terminal point minus the initial point, right? So when we're calculating the components of our vector, notice it's 3 minus 1, it's 7 minus 4. It's the coordinates of the terminal point minus the coordinates of the initial point. So vector AB can be represented by vector OP, where P, the terminal point, is located at coordinates 2, 3. And then we can write vector V, or say that vector V has components 2, 3. Because if the initial point is at the origin, the terminal point, having the same horizontal and vertical components as vector AB, would have horizontal components 2 and vertical component 3. So we can represent vector V and represent all vectors that have the same horizontal and vertical components with vector V having components 2, 3. Now, again, this is going to make it just a little bit easier to do some of the calculations we talked about before, because now, if I'm going to find the magnitude of that vector, we said that would represent all vectors that have the same magnitude. I can use our basic calculation, our basic formula, our Pythagorean theorem, to find the length of the vector. All right? So the magnitude of our vector we can find for vector V having components V1, V2. Then the magnitude of vector V, and this is from our formula from the last section, the magnitude of vector V is the square root of V sub 1 squared plus V sub 2 squared. All right? That was our A and B, square root of A squared plus B squared, if you wish. All right, so for example, from above, our vector V having components 2, 3, and again, please be careful with the notation. When you're identifying a vector, make sure you're using that symbol, not the parentheses. So this vector V having components 2, 3, has a magnitude of square root of 2 squared plus 3 squared, 4 plus 9, or 13. Right? So it's nothing new as far as what we're doing there. It's still just the magnitude of the vector. But in this case, it's the idea that this vector V represents all vectors that have the same horizontal and vertical components. And so, of course, they all have the same magnitude. Now, operations on vectors, again, this is not going to get too deep. We're just going to touch base with it a little bit. Excuse me. But yeah, just to get a little bit of experience with this. If you're heading into calculus, I tell y'all with a lot of this stuff, you're heading into calculus or Calc 2, we do a lot more with the vectors and a lot more, with these things that we're talking about in this latter part of Chapter 8. We get into a lot more of that, a lot more detail with those concepts. So, if you're heading in that direction, we'll talk more about that then. So for now, we're just kind of scratching the surface, giving you a basic idea of how this stuff works. So I'm looking at operations on vectors. Now again, remember there's a difference between a scalar quantity and a vector. Right, a scalar quantity, remember, is just a value. It's a number. It's a constant. It has some measurement. And then there's our vector, right, which has magnitude and direction. So in this case, scalar multiplication, first of all, we'd say that for a real number k, so k is going to represent our constant, that's our scalar quantity. and a vector v having components v1, v2, the scalar product of that constant k times our vector v is given by k times v, or k times the components of that vector v1, v2. And notice all we're doing is multiplying our k value times each of the components of the vector. So, it's a pretty straightforward calculation, but what am I doing? I'm multiplying a vector times a scalar quantity. Right? And so it's just a matter of multiplying each component by that k value. So what you're looking at then is a vector, this vector k times v. We say it's a scalar multiple of vector v, whose magnitude would be then k times that the magnitude of vector v, because basically what we've done is we've taken vector v, multiplying it by a constant makes it that many times longer, right? And so its magnitude should be whatever the magnitude of v is, times k. Now vector kv is in the same direction as vector v if your k value is positive, right? So if I'm, in other words, if I multiply my vector by a positive scalar quantity, then I get a vector that is k times longer than my vector, but it's still in the same direction as my vector. But we could also multiply by a negative k value. And if I multiply by a negative scalar quantity, then I get a vector that again is k times longer than my original vector, but it's going to be in the opposite direction. So for example, I've got vector v having components negative 3, 5, and vector w having components 4, negative 1. And we're just going to do a couple of basic calculations. Let's find 3 times v, and let's find negative 4 times w. All right. But again, these are pretty straightforward calculations. There's nothing fancy here. Here's vector v having components negative 3, 5. And if I want negative 3 times v, then again, it's simply a matter of multiplying each component of the vector times your scalar quantity. I'm not going to call it distribution because that's not what it is. Don't treat that as parentheses and say, oh, we're just distributing the 3. What are we doing? We're multiplying each component by that constant. So 3 times the first component, negative 3, gives me negative 9. 3 times the second component, 3 times 5, gives me 15. And so this vector 3v would have components negative 9, 15. Okay? And again, it's a vector in the same direction as vector v. It's just 3 times as long as vector v, or its magnitude would be 3 times the magnitude of vector v. Right, so there's nothing more to it than that. Negative 4 times w. So here's our vector w having components 4, negative 1. Negative 4 times w. Again, I'm multiplying negative 4 times the components of our vector w. So negative 4 times 4, negative 4 times negative 1, giving me the vector whose components are negative 16 and 4. And this would be the vector negative 4 times w. Now, two things. That vector would have a magnitude that is 4 times the magnitude of vector w. But then because we multiplied by a negative constant, negative scalar, that vector would be in the opposite direction of vector w. So it would be pointing in the opposite direction. Okay. Vector addition. Right? We spent a lot of time in the last section talking about vector addition. We said that was one of the main concepts where we apply multiple vectors to a situation, and we're interested in the net result, right? What is the outcome of the application of multiple vectors, 2 vectors in our case. Vector addition here, when we're using the components of the vector, again, becomes a little bit more straightforward. If I have vector u having components, say u1 and u2, and I've got vector v having components v1 and v2, then the sum of those vectors, maybe we call that the resultant vector, and I'm still just adding 2 vectors, u plus v, so our resultant vector, notice I can get the components of the resultant vector by simply adding the corresponding components of our 2 vectors, right? So vector u plus v has a horizontal component, of u1 plus v1 and a vertical component of u2 plus v2. So again, it's fairly straightforward. I'm just adding the corresponding components. So for example, from above, if I take vectors v and w that we just worked with, and if I want to find the resultant, remember that's our resultant vector. Too many pins to switch back and forth between. When we're looking for v plus w, remember that's our resultant vector. Then again, I'm just going to add the corresponding components. So vector v again had horizontal component -3, vector w had horizontal component 4, vector v has a vertical component of 5, vector w has a vertical component of -1. And so -3 plus 4 gives me 1, 5 plus -1 gives me 4. Here is our vector 1 having components 1, 4, which is the resultant vector. It is the sum of vectors v and w. Vector subtraction is just as straightforward. And so for vector v again, components v1, v2. The opposite, or what we also call the negative of vector v, is negative v, or opposite of v, having components opposite of v1, opposite of v2. Right? And so again, I mean, all you're doing is multiplying vector v by the constant multiple -1. Right? So if we just multiply each component by -1, we get opposite components. Right? But we call this the opposite of vector v. It's also called the negative of vector v. So then with vector subtraction, u minus v, now we could represent subtraction just as you always do. I mean, subtraction, remember, is addition of the opposite. So this is still vector addition, but u minus v is vector u plus the opposite of vector v. Right? But it's still, I'm subtracting u minus v, so I'm going to take the difference of our components. Right? So u1 minus v1 and u2 minus v2. Right? There is also what is called a zero vector. This is denoted simply as 0. It's the vector who has its initial and terminal point at the origin. All right, so if both the initial point and the terminal point are at the origin, then the magnitude of that vector would be 0. And it would have no direction, right? So essentially it's just a point located at the origin, but it's the same point for initial and terminal point. But if we want to represent that as a vector, right, instead of just a point, then we'll call it the 0 vector. And it has no direction, right? Because again, it's just at that point at the origin. Here are some properties of vectors. And again, we're not going to really work with a bunch of this, but again, just to give you the idea of how these work. Properties of vectors. Now, you do one thing to be careful of when you're doing calculations with vectors. There are two quantities involved here. There's the vector quantity, and there's also the scalar quantities. Remember, a scalar quantity is just a value. It's a measurement of some value, some quantity, as opposed to the vector, which has the magnitude and direction. So properties of vector addition and scalar multiplication. For all vectors, u, v, w, in our case representing those three vectors. And for all scalar quantities, b and c. So I'm using b and c to represent scalar quantities. Number one, we've already addressed this one in the last section. We said vector addition was commutative. So u plus v is equal to v plus u. That's vector addition. So it doesn't matter which order I add vectors, I get the same resultant vector. Number two, it turns out that vector addition is also associative, right? The grouping property. So how I group the vectors when I'm adding. So u plus v plus w, u plus v plus w give me the same result, or same resultant vector. Now you have to be a little careful with number 3, 4, and 5. But again, I'm using 0 in different contexts here. So number 3 is the vector v plus 0. Now, when I'm adding, I can't add a vector and a scalar. Now, we talked about scalar multiplication where I can multiply a vector times a scalar quantity, but there is no such thing as adding a vector and a scalar. I can add two vectors, right, which we've done, to get a resultant vector. And number three, now this should make sense. I mean, visually, I mean, nothing different than what we always say with addition. I'm taking vector v and I'm adding 0 to it. I still have vector v. But in this case, that 0 is representing our 0 vector. Right? So it's the sum of two vectors. Number 4, same thing. Here's 1 times v. And in multiplication, now there is such a thing as vector multiplication. And there's actually two different types of vector multiplication. We're not going to get into that. That's later in this section, but I'll spare you that this semester. Here, we're just multiplying a vector by the number 1. So that's just a constant multiple, right? So again, multiplication in our case involves multiplication of a vector and a constant and a scalar. So 1 times v, of course, would give me vector v. Right? If I multiply vector v times 1, I get the same vector. 0 times vector v. Right, now again, in this case, I'm talking about the number 0, the constant 0. So scalar multiple, 0 times v. And if I multiply v times 0, as would be true in any multiplication with 0, I end up with 0. But the 0 in this case, the second one, is the 0 vector. Right? So in other words, if I multiply a vector times a constant, the result is still a vector. Right, so there's some little trickiness there, and I said if you end up in Calc 2 and we do some more of this vector stuff, we get more into all of that and these calculations with vectors. So bottom line, I can add vectors, I can subtract vectors. I cannot add a vector and a scalar. I can multiply vectors. And again, there's two different ways that can happen. I can also multiply a vector times a scalar. That's what we keep calling scalar multiplication. But when you multiply a vector times a scalar, the result is a vector. And again, just for future reference, when you multiply two vectors, there are two possible outcomes. You could actually get a vector, or you could get a scalar. Right? And so again, that's later in this section. If you're interested in that, you can look through your text and see that. But again, Calc 2, we'll talk about that. Number 5, that is the sum of two vectors. And this is the one we had mentioned earlier. If I take vector v and add its opposite, because remember, vector v and the opposite of vector v, they're going to have the same magnitude. They're just in opposite directions. So if I apply, think of it back when we talked about like applying forces on an object. If I apply the same force on an object, but in opposite direction, right? If somebody pushes on the object from one side and somebody else pushes on the opposite side, but they're pushing with the same amount of force, what's the result? Right? What's the resultant vector? It would be 0. All right? Nothing's going to happen. It's not going to move. But again, in this case, it is a vector because I'm adding two vectors. The resultant is a vector. Number 6, number 7, number 8, that addresses like combinations of vectors and constants or scalars. Number 6 is, again, an associative property. Notice, again, B and C are scalars. V is a vector. So I've got the product of B, C, and vector V. And in either case, those would give the same result, right? Because again, in number 6, C times V would be a scalar multiple of vector V. And then I'm multiplying times B, which again is a scalar multiple of that vector. Here I've got B times C, which is again just the product of two scalars. And then multiplying by V gives me a scalar multiple of vector V. Number 7 looks like distribution, right? But like I said, it's kind of the same basic idea for our purposes. So number 7 here, we're adding two scalars. That'll give you a scalar quantity times vector v, gives you a scalar multiple of vector v. On the right side, this is a scalar multiple of vector v. This is a scalar multiple of vector v. But in either case, I get the same resultant vector. And then number 8, that's the sum of two vectors, which is a vector, times a scalar. That's a scalar multiple of that vector. On the right side, that's a scalar multiple of vector u. That is a scalar multiple of vector v. The sum of those is a resultant vector. Right? Now again, we're not going to really do much with a lot of this, but it's just to give you the idea of how calculations work with vectors. This I'm interested in, though. This serves a little bit of a purpose. What we call a unit vector. A unit vector is a vector with a magnitude of 1. Right. So any vector that has a magnitude of 1 is called a unit vector. For a non-zero vector v, the unit vector in the direction of vector v can be found by multiplying the vector times 1 over its magnitude, or we could say dividing the vector by its magnitude. But this is scalar multiplication. That's what this is. So I'm calling my unit vector u. It's the vector in the same direction of vector v, but having a magnitude of 1. And I can find that vector by multiplying v times 1 over its magnitude, or again, simply dividing v by its magnitude. But all that is scalar multiplication. I'm multiplying by the reciprocal of its magnitude, which is the same as dividing by the magnitude. So for example, find the unit vector. This is a question I would be interested in for a test. Find the unit vector in the direction of vector v, which has components 3, 5. And so vector v having components 3, 5, looking for the unit vector in the same direction as v. First thing we'll find is the magnitude of v. All right, and again, I can just use our square root of a squared plus b squared, or the square root of the sum of the squares of the components. So square root of 3 squared plus 5 squared, 9 plus 25, square root of 34. That's our magnitude of v. So then our unit vector in the direction of v would be the scalar multiple of vector v, where I multiply by 1 over the square root of 34. Or again, I'll simply divide each component by the square root of 34. So the components of vector u, the unit vector, in the direction of vector v would have components 3 over square root of 34 and 5 over the square root of 34. And you don't have to worry about rationalizing denominators there. You can leave that as that. That's fine. Now, just to prove that this is true, we said that would be the unit vector in the direction of vector v. And since it is a unit vector, its magnitude would have to be 1. So notice, if I calculate the magnitude of vector u with components 5 over the square root of 34, or rather 3 over the square root of 34 and 5 over the square root of 34, and I plug that into our square root of a squared plus b squared. 3 over root 34 squared gives me 9 over 34. 5 over square root of 34 squared would give you 25 over 34. 9 34s plus 25 34s is 34 over 34, which is 1. And of course, the square root of 1 is 1. So that would be the magnitude of that vector u. That checks out from what we said. All right? So finding the unit vector in the direction of our vector. That actually has a lot of uses in this context of vectors and things that we do with vectors or calculations. One of which is representing a vector in a different format, what we call linear combinations of unit vectors. So the unit vector parallel to the x-axis and the y-axis. These are of particular interest to us. They're useful, defined to be vector, or what we call vector I and vector j. Vector I has components 1, 0. Vector j has components 0, 1. Let me just elaborate on that for a second. So we're calling these the unit vectors along the x-axis and the y-axis. All right. So what we're calling this vector, let me shrink that a little bit. If I look at the point along the x-axis, x coordinate 1, point along the y-axis, x coordinate 1. This unit vector that we're calling vector I would be this vector. It's the vector along the x-axis whose components are 1, 0. And then this vector that we're calling vector J is the vector along the y-axis, having magnitude of 1. Right, so it's our unit vector along the y-axis, so the components of J would be 0, 1. Right? So when we talk about the I vector and the J vector, those are the vectors that we're referring to. Now, here's one use for these guys. Any vector can be expressed as a linear combination of unit vectors I and J. Now, all I'm really interested in is the output of this, but look what happens here. I'm going to take a vector V having components V1, V2. Then I could represent vector V as the sum of the vectors having components V1, 0 and 0, V2. So in other words, if I add these two vectors, V1 plus 0 is V1, V2 plus 0 is V2, I get the vector whose components are V1, V2. Now I can then take these two vectors, V1, 0 and 0, V2, and I can express V1, 0 as the vector V1 times vector 1, 0. And notice again, I'm just multiplying V1 times 1 to get our quantity, our horizontal component. Now remember, V1, V sub 1, and V sub 2, those are just the components of our vector. Those are just scalar quantities. I think I called it a vector earlier. V is a vector. V sub 1 and V sub 2 are its components, which are scalar quantities. So when I look at this is a scalar multiple of our I vector, whose components were 1, 0. This is a scalar multiple of our J vector. Right? But ultimately, it's the horizontal component of vector V times the I vector. It's the vertical component of vector V times the J vector. So you can take then a vector having components A, B. In this case, I've got vector V having components 3, -4. And I can express that vector as a linear combination of the unit vectors I and J. I can represent vector V using 3i plus -4j, or 3i minus 4j. So what that does is it gives you another way that you can represent your vector. So we have the component form of the vector, components 3, -4. And we have the linear combination of vectors I and j, 3i minus 4j. But either way, those represent the same vector, it's just different notations. Okay? And as with, we've seen before with situations where we've had different notations that we use for different quantities, each one has its advantages and uses. So representing the vector in component form, 3, -4, maybe has its uses or advantages in some cases. Representing the vector as a combination of I and j, 3i minus 4j, also has its advantages in certain calculations. Right? So again, that would be something we'll explore further down the road. You could also take it in the opposite direction, obviously. So if I take this vector w, written as a linear combination of I and j, -2i plus 5j, then I'm looking at this vector w whose horizontal component is -2, vertical component is 5. So I can represent it as the vector with components -2, 5. Right? So it's just another way that we can represent our vectors. Direction angles. I'm going to finish with this. I'm just going to give you a little bit of description here. Again, not something that we're going to do anything with formally, but it is something that kind of ties back to the whole trig idea. I mean, this is trig after all. Let's take a terminal point P. For our vector in standard position. And more specifically, it's a unit vector in standard position. All right, so this vector u in our diagram, initial point at the origin, terminal point at point P, it is a unit vector, which means its magnitude is 1. And if its magnitude is 1, then that terminal point P would have to be a point on the unit circle. Now this will tie back to some of the things we've talked about, back to our unit circle connection or definition with our trig function values. All right, so since vector u is a unit vector, its magnitude is 1, then that terminal point would lie on the unit circle. And if you remember back to our unit circle, the points that lie on the unit circle, they have x and y coordinates that correspond to the sine and cosine of the angle theta in standard position. All right, so this will, kind of ties things back full circle to where I could then represent the components of my vector. Horizontal component would be equal to cosine of theta. Vertical component would be equal to the sine of theta. Those are the coordinates of our points on the unit circle, which the terminal point of this vector would lie because it's a unit vector whose magnitude is 1, right? That's the radius of the unit circle. So in this way, the unit vector can be expressed in a different component form. And if you even think back to this, we kept doing that conversion with A and B. We said A was R cosine theta, B was R sine theta. But what's R in this case? R is 1. So A was equal to 1 cosine theta or just cosine theta. B is equal to 1 sine theta or just sine theta. So there's even another way that you can represent your vectors. And again, this ties it back to the whole trig idea. So this is a linear combination also of our unit vectors I and j. So if the components of our vector are cosine theta, sine theta, then I could also represent u as cosine theta I plus sine theta j. Now again, the I here is not the imaginary unit, right? The I here is simply representing that unit vector along the x-axis. J represents the unit vector along the y-axis, right? So this has nothing to do with complex numbers, it's simply notation. So the corresponding, or for the components of u, are now functions of what we call our direction angle theta. Right, that's our theta in standard position. Remember, in terms of vectors, we called it the direction angle. And we could say now that u has components that are functions of the direction angle. Right? So then we could go on and talk about all of that, in terms of if I know the direction angle, I can find the components of the vector, vice versa, right? That type of thing. But again, just a little bit of an intro there. I don't want to get too deep into this. We'll kind of leave it at that. But I am interested in these different forms of the vector, where we can take a vector, write it in component form, or write it as that linear combination of the unit vectors I and j. So that's where we're going to stop in section 8.6.